So what we're going to do now is we're going to take a look at an interesting programming example that's in my GitHub repository. If we go over to this link here in my live lessons Reactor 2 EX2 folder, you will see the example that we're going to walk through here momentarily. So this example is pretty cool. It essentially shows how to implement 3 different algorithms for finding the minimum values in an unordered list. And of course, since we're talking about Project Reactor, it does it using Project Reactor features. And this will demonstrate using fluxes and monos, which of course are the reactive types in Project Reactor. And what it's going to do is it'll essentially try to find the cheapest flight or flights from a bunch of available flights. And this also shows some other really cool features like async task barrier framework and other operators that can be used to do conversions of various things in interesting ways. So let me first go ahead and start the program running so you can see what it's supposed to do. So we click on that and that'll start it running. It takes a while to run, so I'll let it run in the background while it's. So what we're going to do here is we have this little test data factory that has a whole bunch of information about flights, when they depart, when they arrive, where the airport it's leaving from, where the airport it's going to, the price, the airline, and the currency type. So British pounds, US dollars, euros, and those are the three types we're dealing with here. Of course, we could add more if we wanted to. So we have a little program here that basically generates data to show off the different algorithms. And then the algorithms are going to go off and try to find the minimum prices and do some other cool things using reactive programming. There's a couple interesting little methods here that are fun. There's one called find flights. It takes something called a trip request. A trip request is basically what the user wants to find the flights to where they're going. So here's an example of a trip request. We're going to leave on this date, and we're going to basically arrive at this time. And here is the airport we're leaving from and the airport we're going to. And the currency is going to be in euros, and we have a single passenger going. So there's a trip request data type over here. I won't spend a whole lot of time on it. That basically has the departure date time, the return date time, the airport leaving from, going to, et cetera, et cetera, et cetera. So lots of stuff in there. This shouldn't be too surprising. It's just a good plain old Java data type. If we take a look back at our test data factory, we take a bunch of flight information. So we have flights, and you can see that flight is another data type over here. And this has, departure date, arrival date, time, return, departure date, return, arrival date, departure airport, price, airline code, what currency the thing's in, et cetera, et cetera. And again, this is just kind of a plain old Java object that we use in order to do to return information that matches the trip request that somebody makes. And we concatenate all this information together. This is just using good old Java streams. Here's a really clever method called concat stream that takes a list and uses a Java stream to concatenate the contents of the list n times. And I won't spend a whole lot of time on this other than to say it's a pretty cool little capability you can do with Java streams. So we go ahead and we build up a stream of strings that correspond to this flight information here. And then we map it into a flight object, and we get rid of everything that doesn't match the trip request, and then we return that as a list. So that's just kind of getting us data. There's innumerable other ways we could have gotten data. This is just a fun example of demonstrating some streams in interesting ways. So let's pop out of that. And let's go back to the program. So what we do is we go ahead and we make ourselves a list of flight objects by using our test data factory find flights method, which goes ahead and finds everything that matches the trip request. And then once we've got that, we're going to go ahead and we're going to run a bunch of programs. And these different algorithms, the program algorithms, are going to find the cheapest flight using a bunch of different techniques. And for various reasons, I use something called the async task barrier. I'm not going to spend a lot of time on that right now. If you take a look at some of the later videos in the reactive programming part of the course, it'll explain this in more detail, and we'll cover it in other parts of the course. It's not really used in any profoundly interesting way here. It was just a way to get everything up and running. And so what it does is it's going to go ahead and call this run test method, and then it's going to pass in a method reference to run test, and that's what's actually going to do the computations. And the async task barrier will block while all the tasks are running, and when we're done, we get the results. And it'll also tell us which of the algorithms took which amount of time to run. So if we go over here, you can see we finished our computation, and you can see we searched for the best price for this particular flight, and we came back with a flight that matched that cost 45 euros, pretty cheap, and that's on British Airways. And you can see each of the algorithms computed the same result, which is a good sign, but they took different amounts of time to run. And that's really what we're going to be focusing on, the algorithms and their expressions in reactive programming feature framework capabilities. So you'll see that the one pass algorithm executed the fastest. No big surprise there because it's a one pass algorithm. There's another algorithm that uses two passes, computing the min, and that took longer because it's doing two passes. And then there's yet another algorithm that sorts the data and then goes ahead and figures out which ones are the min prices because they'll be the first in the sorted stream. And that takes a little bit longer because, of course, we have to sort the data. And as you're probably aware, sorting is an n log n operation, whereas doing two passes is going to be probably less time consuming than sorting. And of course, doing one pass is the fastest way to do this. And so we'll take a look at those different algorithms and see how they work. But I just wanted to give you a feeling for the performance of each of the approaches before we look at them in detail. Here's the run test method. This takes a function that is passed a list of flights and returns a mono to void. We'll talk about the mono to void later. The first thing we do is we make a deep copy of the flight list. This is the list of all the flights that the system knows about, because we're going to be doing operations that are mutating on this list, and we don't want to affect the underlying list. We want to be able to share that list across the different algorithms, but have copies for each one. It is surprisingly awkward in Java to do a deep copy of something. In fact, as far as I can tell, it's next to impossible. Maybe not impossible, it's too strong. You could probably use reflection if you really put your mind to it, to do a deep copy in a generic way. So I had to write my own little deep copy algorithm and stick it away in a library. So we make a list, an array list with a certain amount of size, the list we're copying from, and then we use a for each loop to iterate through every element in the list. And we make a new element and add it to the temp list, and then we return the new list. We probably also could have done a Java 8 stream approach here too. I just was making my life easy and just doing good old-fashioned accumulator approach. In fact, if we'd used the Java stream approach, we could have trivially parallelized it as well. So once we've got ourselves a copy of the flight list, we then time how long it takes to run this particular algorithm. So we take the algorithm that we passed in, which came as a function, as you can see, and we call the apply method, because Java functions, the function data types are going to be what are called functional interfaces, and the apply method is how you run them. And we give it the flight list, and that's going to then go ahead and do its thing, and we're going to block waiting for the response so we can get an accurate timing, very important here. And then we're going to go ahead and return an empty mono. That's just to synchronize with the async task barrier framework. So all the methods run in that way, and that way we can consolidate how we time each of them, which is kind of nice. And if you want to play around with the run timer time run method, it's just a clever way of being able to time things and keep track of the results. Let's now come down and take a look at the different algorithms. We'll start out with the one that prints the cheapest flight using min. So this is a two-pass algorithm that's going to use min and filter. So here's what we do. We first call a little helper method that all the algorithms use called convert flight prices. And we give this the list of flights and the currency we want things converted into. And let's take a look at this. This is actually a really cool implementation. What we're going to do is we're first going to go ahead and create an object that will handle the exchange rate computation, because of course the results are in dollars, the prices are in dollars and euros and British pounds and so on. And we're going to use this exchange rate service in order to be able to provide the appropriate normalization or conversion into the rate that's wanted by the user. In this particular case, it's euros, but it could be dollars or pounds or whatever. So we do that in parallel. We make one of these objects. And then also in parallel, we're going to go ahead and create a flux. So we're going to convert the flight list into a flux stream, and we're going to go ahead and make ourselves the exchange rate object. Now, in this particular example, those are not going to take very long to do, but you can imagine if this was written using microservices, it might take longer to create things that we might want to use later. So what we then do is we use the exchange rates mono. That's what this thing is. It's mono is basically kind of like a completable future. And we say, once the mono has finished being created, once it's asynchronously finished running, then use the flat map many method. And flat map many is a very interesting method that it's commonly used to convert mono results into flux results. And what we're going to do here is we're going to take the flights that we have, the flights flux that we got back here, and we're going to call the convert currency method on each of the flights, passing in the currency we want to convert to, the flight, and then the rate exchange service. So those things are passed into this thing called convert currency. And what this does is it checks to see if we even need to do anything at all. Whether we have to check to see if we have to do any conversion. If we have the price in dollars and we're trying to convert to dollars, it's a no-op. So we just return the object untainted. But if it's in dollars and we want pounds, or it's in dollars and we want euros, we have a conversion to do. So in that case, we go ahead and we use the rates service to get the rate for the currency that we're converting into. And then we go ahead and take that rate and we multiply it by the price. And that gets us the new price. And so we set the price, and we also set the currency in the flights object to reflect the fact it's now in a different currency. Okay, so that's just a little helper method. Again, not too profound at all. But what's interesting about this particular approach is it waits for both the exchange rates computation to finish and the flights computation to finish. And then it goes ahead and computes a flux. And that's what gets returned from flat map many. So it converts the mono into a flux result by multiplying every flight by the rate that's appropriate. And then the last thing we do, and this is very, very important, we take that flux and we turn it into what's called a hot source or a hot flux. There are two different types of fluxes in Project Reactor. There's hot sources and cold sources, or hot fluxes and cold fluxes. The cold fluxes will start from scratch every time and recompute whatever stream from the beginning. So that's important for some operations. In this case, we didn't want that. We want to be able to have a hot flux. And what that means is that you can read from it and then later use it again, and it won't start over from the beginning. It'll start from wherever you left off before. And that turns out to be important for some of the algorithms. Okay, so that's basically the convert flight prices method. And you can see what it does is it returns a flux of flights, which we call flights. So now we've got a flux of flights. What we're going to do now is we're going to use a helper method from a library called MathFlux, or package called MathFlux. And we're going to take in the flux of flights, and we're going to go ahead and find the prices. So we're going to end up basically returning the minimum priced flights. So it'll come back as a mono. It'll figure out what is the cheapest value, in this case, the price, in that particular flux of flights, more generally in that flux of whatevers. So now we know what the lowest price is. And now we use flat map many again. And what we're going to do is we're going to take the min value that came out of the min method here from MathFlux. And once we have that, once that computation is done, we're then going to use the min in order to be able to filter and only allow flights that match the cheapest price. Keep in mind, this is an unsorted list or unsorted flux string. So we're going to go ahead and find the minimum price items. Everything that matches the minimum price will be allowed through. And so we'll end up with a flux called lowest prices. And when we're done with that, we call the print results method for lowest prices. You can see what that does is it will go ahead and use the do on next method, which is basically a method that is kind of used for debugging. It doesn't really do anything with any side effects. It's called an action operator. And so the action operator will go ahead and print out the results here, which is now going to be a flux list. It'll be not a flux, it'll be a list. We convert that to a list of flights. It'll print that out. And then we'll return a mono. And the returning the mono to void just indicates to the async task bearer, this computation is finished. So that's what we're going to do. That's how we do print cheapest flights min. And you can see here that we do it entirely asynchronously. And these computations basically chain together. So it's very much like Java Streams, kind of combined with Java completable futures, if you're familiar with completable futures and the asynchronous capabilities that they provide. So that's print cheapest flights min. You can see it's a two-pass algorithm because first we have to go find the min. So that requires one pass. And then once we have the min, then we go ahead and we use filter to look through all the items and find everything that matches that min. And that's what gets returned. So now let's take a look at another implementation. This one, as you can see, is the slowest, but it's got some interesting things that demonstrate some cool features of Project Reactor. So what we're going to do here is we're once again going to call convert flight prices and get ourselves a flux of all the flights that match the currency that we have here for the trip. So it's going to basically get us all the flights that we want in that currency. So it'll put them into the currency. And then we're going to go ahead and call the sort operator. So sort is a kind of a transforming operator, of course, and it's going to order the flux stream based on the comparator. And in this case, it's the price. So that will sort the contents of the flux stream from lowest to highest price. Well, at that point, it's pretty easy to figure out what the min element is because it's whatever is in the beginning of that flux stream. So what we do then is we go ahead and say sorted flights, which is a flux of sorted flights, take one. And take is essentially what's called a suppressing operator, and it just gets the first item, which in this case is the cheapest one because we sorted it. So once we have that then becomes the min. And now we're going to use the flat map operator, which is another transforming operator. And we're going to look through all the sorted flights because they're sorted. And we're going to use the take while operator, which is another operator that it's kind of a short-circuited operator. It'll keep running while the elements match the predicate. So as long as things match the minimum price, we keep consuming it and letting it be emitted from the flux stream. So what we end up with, again, is it's another form of a sort of a suppressing operator. It'll end up giving us back a flux of just the lowest prices. And we know that we can stop as soon as we have something that doesn't match because the flux stream is sorted. So it'll keep going as long as we're equaling the min price. And then we go ahead and print the results again, except this time we say we're using the print cheapest flights sorted algorithm instead. So the third and final algorithm is really the coolest one in my mind. It's also ridiculously concise for reasons you'll see in a moment. And as you can see from looking at the results, it's also the most efficient algorithm because it only makes one pass. So of course, there's less going on, whereas the other algorithms were either two passes or one pass sorting followed by just selecting the items that happen to be the lowest. So let's go ahead and do print cheapest flights one pass. And we start out by converting the flight prices, so they're all in the normalized currency. And then we're going to collect everything. So this is another, it's called a terminal operator. It's part of Project Reactor. It's very similar to Java Streams and the collect operator there. In fact, you can use Java Streams collectors to implement this, as I do here. And what that's going to do is it's going to essentially collect into something that I wrote called the cheapest price collector, which we'll look at in a second. And as you might expect, the cheapest price collector is going to keep track of what the min value is, and it'll collect the results. So we'll have all the min values, and I'll look at that implementation in a second. When we're all done, we've got ourselves a mono to a flux, and we just use flat map many, as is often the case with function identity, to go ahead and essentially de-encapsulate, if you will, the flux out of that mono. And so we end up with a we end up with a flux of the lowest prices, and then we go ahead and print those results out. So let's take a quick look at the cheapest price collector. The cheapest price collector is a Java collector. It's got a factor method that makes an instance of the cheapest price collector. And if we go look here, there it is, lo and behold. So cheapest price collector implements collector. That's the Java Streams framework standard way of making a collector. And it's basically going to take a stream of flights, and it's going to store them in a list of flights, and it's going to return a flux to a stream of flights. So that's how it works. It keeps a local field called min, which is going to be the minimum value that the collector's seen so far as it looks at all the flights that go whizzing by. The supplier is going to be making a new array list. That's what we're going to use as the so-called mutable result container. The accumulator is where all the interesting stuff gets done. So the accumulator is called every time there's a new flight to keep track of, to examine, to collect, potentially collect. And what it does is it takes the array list of lowest prices and the latest response that we've got, which is a flight. And if the price of the response is less than the min that we've been computing so far, so if we found a new min, we clear the lowest prices accumulator. We add this response to the lowest prices. So now we have the first element there. And then we update min to be the price of that trip response. So that's how we start getting a new min. Otherwise, if the price equals the min, this is a duplicate, or not a duplicate, it's another price, it's another flight that has a price as low as the min that we've seen so far, in which case we just add the trip response to the lowest prices mutable result container, or that accumulator that we've got. And of course, if the price is higher than the min, we just ignore it because we don't care about things that are higher than the min. We only care about things that are lower than the min or things that equal the min. So you can see, if you kind of think about this algorithm is a single pass. It goes through all the elements in the stream and basically updates this local field and uses that to know when it needs to either update the lowest prices container or when it needs to make a new container and start again from scratch because we've found a new min. There's a couple other methods here that the combiner, don't worry about that. That's a parallel streams thing. We don't use parallel streams here. The last method that's fun is the finisher. And finisher is a special method that's used after all the computations are done. And it can be used, it can either be a no-op if no conversion is necessary, or in this case, what we use the finisher for is to take the list of flights, which is this internal accumulator, or what's sometimes called the mutable result container, and it's going to automatically convert it into a flux stream. So that's how we get a flux stream as the result of all this stuff. And we don't need to worry about the characteristics. They're whatever they are. We don't care. So basically, that's the lowest price or cheapest price collector. And you can see some interesting things, how this works. It's kind of demonstrating how you can combine Java Streams mechanisms with Project Reactor mechanisms. In fact, Project Reactor builds off of Java Streams in a very nice way. In fact, Project Reactor builds off of modern Java in a very nice way, which is an improvement, I think, over what you would get if you were to work with RX Java, which does not do as good of a job dealing with modern Java. It's really stuck more in Java 6 with emulated stuff to make it look and feel a bit more like modern Java. So those are basically the things I wanted to cover in this particular example. Oh, one more thing real quick. The exchange rate service, it's really very simple. We have a map that maps the currency as a string to a map that maps the currency to the exchange rate. And you can see here, I just did a very simple implementation. Obviously, a real implementation would go talk to a microservice somewhere that does exchange rates. And in this particular case, we just keep track of the relationships between dollars, pounds, and euros. And I just sort of made some stuff up. These are not accurate. I think at the moment, the euro and the dollar are basically 1-to-1, which is probably not a good sign if you're trying to vacation in the US this year from Europe, because it means you're paying more. But I think the pound is still worth more than the dollar, if I'm not mistaken. Any rate, so just some interesting stuff that demonstrate how you can make a very simple exchange service. Okay, so that's the example I wanted to walk through. There's a lot more stuff here that we'll cover in later parts of the course, like the async task barrier. I didn't really use it in any profound way here, so I didn't want to focus on it. But we will show some examples later that really get into the power of the async task barrier, which is used for all kinds of interesting things, not the least of which is testing of asynchronous reactive programs and asynchronous reactive methods in reactive programs in order to make sure that all the computations finish before the main function exits.